Welcome to lesson on chapter 5.4, Equations and Graphs of Trigonometric Functions. We've seen everything that we're going to use in this lesson before. It's just sort of pulling everything together. So we already know how to solve using our unit circle on specific or restricted domains, how to solve trigonometric equations. In our previous lesson, we saw how to use our K notation to indicate an infinite set of solutions. And so now we're going to pull them together. So when we talk about general solutions of trigonometric functions, what we mean when we say general solutions is I want to have a solution that shows me all of the infinite possibilities. So every single possible solution that might exist. So let's start and we'll solve this function. We'll take a look at a graph to see that things are making sense, and then we've got a couple more examples for us to work our way through. So the first thing that I'm going to do is I'm going to add the 8 to both sides. I'll divide by 16, and so that leaves me with a half. I take the square root, and so I get sine of theta. Don't forget that we get both the positive and the negative root here. Now, if I simplified that, that would give me 1 over root 2. I'm going to rationalize it by multiplying by root 2 over root 2, which leaves me with plus or minus root 2 over 2. Looking at my unit circle, I know that I get positive root 2 at pi over 4 and at 3 pi over 4, and I get negative root 2 for sine at 5 pi over 4 and 7 pi over 4. So I'm just going to write those angles in here. And 7 pi over 4. Okay, so sometimes it helps to start writing a set and seeing how the solutions are going to continue or are going to carry on. If I kept going, right, I would keep going either up by pi over 2 or down by pi over 2 as I work my way around the unit circle to keep getting to the next solutions. I'm not restricting myself only to 0 to 2 pi or to any other domain. I want to look at all the possible solutions. So the way we normally do this is we start with the smallest positive angle, and then we look at the patterns that could exist. Now, in this case, because all of these solutions are separated by pi over 2, I only have to write one set for my solution. Sometimes we're going to have 2 statements we're going to need to write to show all of the possible solutions. But I can find a solution at pi over 4 and every pi over 2 after that. So we write pi over 4 plus pi over 2k, where k is a member of the integers. And again, that means any integral multiple of pi over 2. So added or subtracted to pi over 4 will get me another solution. If I jump over to Desmos, I think I already have my graph up for this one. So we can see that we've got those points labeled already. I'll add a couple more into my graph, and you can see this is a graph of 16 sine squared minus 8. Equals y, and then of course if we're looking for the solutions, we're looking for the roots of it. So I have a whole bunch of the roots labeled for us, and we can see our pi over 4, then our 3 pi over 4, then our 5 pi over 4, then our 7 pi over 4. Just because of where the labels went, they're not necessarily always in order. But we've got them all there, and you can see if I keep going, my next one is going to be at 9 pi over 4 as I go another pi over 2 above. If I work my way backwards, then I hit my negative pi over 4 and my negative 3 pi over 4. Okay, let's jump back into our notes here. Okay. Take a look at example number 2. We're going to come up with a solution for this in both radians and degrees. So this is one of the ones where we're going to have to factor first. So I'm going to do a little factoring by inspection here. I know I'm going to have a sine theta as my leading term in both of them. I'm going to have a 2 and a 1. Excuse me, my sum is positive, so I want a plus 2 and a negative 1. So that leaves me with two equations. I get sine theta minus 1 equals 0 and sine theta plus 2 equals 0. Well, this one's actually relatively straightforward. I'm going to start with the second one first. There are no solutions, right? There are no solutions that exist where sine of theta is equal to -2. If I've got my unit circle, -2 is down there, and there is no intersection with that point. However, if I look at where sine theta is equal to 1, we're going to find that at pi over 2. Now, we know that this point will repeat every time I go around the circle. Now, I could go in positive rotations or I could go in negative rotations. So it's going to be every period thereafter, I'm going to get a solution. So the solution for this example is going to be theta is pi over 2 plus 2 pi k, where k is a member of the integers. There could have been another set of solutions if the other factor didn't have a solution that didn't exist, right? If the other one was, I don't know, sine of theta plus 1 equals 0, then we would also have another set of solutions that would go along with that equation. All right, one more example for us to, oh no, sorry. I almost forgot. We were also going to look at this in degrees as well. Now, in terms of degrees, I just have to pick back up where I'm finding the angle. So if I'm thinking about my unit circle in degrees instead of in radians, that first solution is going to be at 90. The period, of course, has now changed. So because I'm in degrees, the period of my function is 360 degrees. So my solution then becomes theta is 90 degrees plus 360k KEI. And we could do either solutions in either degrees or radians at any point. It's just switching back and forth between the two methods of solving for our angles using our unit circle. You'll notice I'm not using the calculator at this point too. Even though I'm coming up with the infinite set, I'm still just using my knowledge of the unit circle. All right, so last example we're going to look at, we've got a kind of ugly equation to deal with. We have both horizontal and vertical stretches. We have a reflection over the y-axis. We've got a horizontal translation, a vertical translation, and then it's still equal to another value. So there's going to be lots of algebra we have to do to rearrange this and solve for x. And then we're going to double check this in our calculator afterwards. Okay, so first thing I'm going to do is I'm going to subtract the 7 from both sides. And so that's going to give me a -1. I'll divide by 2. So I get cosine of -3 x minus pi over 6 is equal to -1/2. Okay, now I'm going to take the inverse cosine. So I'm thinking about my unit circle, and I'm looking at these 2 points where the cosine is -1/2. So that's going to be at 4, sorry, we don't usually say 4 pi over 6, at 2/3 pi. Just fix this one. So that'll be at 2 pi over 3, and then at 4 pi over 3. Okay, and those, of course, will each occur every period from there. And so we're going to have to think a little bit about how this is going to work. So when I take the inverse cosine of both sides, I still have all the stuff inside the argument, right? It's when I figure out those angles, right? It's going to be 2 pi over 3 and 4 pi over 3. But that's equal to -3 times x minus pi over 6. Now, these repeat every 2 pi k at this point, right? They repeat every period. Usually what I tend to do is then just put the KEI in the middle of it instead of writing it after each line. Okay, so what I'm going to do next is I'm going to take care of both the reflection and the horizontal stretch at the same time. So I'm going to divide both sides by -3. So that gets me x minus pi over 6 is equal to, so I'll get 2 pi over 9, sorry, negative 2 pi over 9. And I will get negative 4 pi over 9. Neither of those are going to simplify. Now I can just sort of combine these two lines together. So I'm going to have plus negative 2/3 pi over k, KEI. Okay, so now what we have to remember, let's jump back up to the top and look at our function for a second. If I look at that b value is equal to 3, I know then the period is 2 pi over 3. So when I think about when and where these solutions are going to repeat themselves, the solutions down here in the line we were just looking at should repeat themselves every 2/3 pi, because that's what the period of the function is. So then the question comes in, if that's the period of the function, does it matter if I add the period or subtract the period? And it doesn't. So even though this is a negative, we divide by a -3, so we have a negative sign in here, we don't normally include that value. Because again, k is an integer, so k could be positive or negative. So we're going to see both, plus 2/3 pi, and we're going to see minus 2/3 pi if k is either 1 or -1. So what we usually do is we just keep this sign as a positive, and we can ignore the sign that's in there already. One of the things that does happen is that both of the solutions that I have are now negative, and we're probably going to switch those back around to positive solutions at the end. The other thing we need to think of before we take our next step is, what is that negative pi over 6? Well, that's our phase shift or our horizontal translation. What's really important to understand is that the horizontal translation, or that phase shift, does not change the period of the function. So when I go to add my pi over 6 to both sides, I'm adding it to the initial solution, but I'm not changing the period of repetition, right? I'm not changing the period of the function. So I'm not going to add pi over 6 to the 2/3 pi. So what I get x is equal to, so if I have negative 2 pi over 6 plus, 2 pi over 9 plus pi over 6, so common denominator there is going to be 18. So I've got negative 4 plus 3, so that's going to give me negative pi over 18. The second one, I'm going to have, it's negative 8 pi over 18 if I convert to a common denominator, plus 3 pi over 18. So that's going to give me negative 5 pi over 18. And then I'm going to have my plus 2/3 pi k, where k is a member of the integers. As we talked about in our previous class, if you're using z here instead of I, that's maybe even better than using I. So the only thing that I might change here is I might switch those two solutions so they're both positive values, and I can do that just by adding 2/3 pi to each of those numbers. So if I convert 2/3, if I convert 2/3 into a denominator over 18, that's going to be 12. So I'm going to get 11 pi over 18, and I'm going to get 7 pi over 18. And then those are both I get my next solutions by adding 2/3 pi k KEI. All right, and that is my full solution. So the thing that's really weird in this solution is this part right here, and we have to actually understand what we're doing when we're rearranging the equation. The fact that the pi over 6 is our horizontal translation and therefore does not change that 2/3 pi, because the 2/3 pi is the period of our function. So let's jump to Desmos. And we'll take a look at what this function is going to give us. So we've got y equals 2 cosine of -3 x minus pi over 6. Get our brackets there. Plus 7 equals 6. And so if we, oh, sorry, I obviously can't put two equations on the same line. So let's get rid of the last little part here. And then we'll graph our line y equals 6. And if we look at our solutions, I can see that there are my solutions of 7 pi over 18 and 11 pi over 18. And of course, one period away from those were the values we initially had algebraically before we moved them to positive rotations instead of negative rotations. Now, if you gave me negative pi over 18 and negative 5 pi over 18, for right now, I would be okay with that because those are correct answers. But convention tells us that we want positive angles. So when we get our final answer down here, we want those values to be positive, and that's why we add that period to each of those. Okay, that is everything for today's lesson. Take your time with this, rewatch it again if we need to, especially that that third example. That third example is about as tough as it gets, but we do need to make sure we understand everything that's going on in there.